I would like to thank Dr. Praveen Kumar for arranging such type of activities for field engineers as well as for uh, teaching faculty of various institutes. So thank you very much. Thank you, Praveen ji. Praveen ji.
हाँ सर, वो संदीप चौधरी जी से बात हो रही थी, वो जस्ट उन्होंने कहा
हाँ हाँ
3-4 मिनट लगेंगे
ठीक
उनको ज्वाइन करने में।
ठीक है ठीक है।
तो जैसा प्रोफेसर माथुर सर ने बताया, हमारे यूनिवर्सिटी डिपार्टमेंट, सिविल इंजीनियरिंग डिपार्टमेंट, दिस डिपार्टमेंट ऑफर्स MTech in 3 disciplines: MTech Structures, MTech Environmental Engineering, and MTech Geotechnical Engineering, with 18 seats. And we are offering PhD programs also in all these disciplines. And at our institute, we have around 140 faculty members offering 12 MTech and 11 BTech programs, and mainly computer science, IT, petroleum, mechanical, electrical, electronics. Every standard branch is being offered, including aeronautical engineering. So this is about our institution. In the meantime, as Professor Choudhary sir joins, I share with his accomplishments and his pages as reflected on the IIT Indore page. So I take your permission to share the screen with the main profile of Professor Sandeep Choudhary. I think this page is visible to everybody as Professor Sandeep Chaudhary. Anybody can unmute? Just a minute. Uh, Anybody can unmute himself and confirm whether this page of Professor Chaudhary's profile is visible to
प्रवीण
everyone.
जी विजिबल है?
Sir,
विजिबल है?
sir. So, Professor Chaudhary ji is currently working as professor in IIT Indore, Civil Engineering Department. Rather, he is a he is working for sustainability engineering since last 10 years in a great way, and he is chairing a committee on Asian Concrete Federation as well, and he has I will just share, he is postdoc research fellow from Korea, and did his PhD from IIT Delhi. He served for long years in MNIT Jaipur, and of course he established the civil engineering department at IIT Indore. We have been knowing Professor Chaudhary ji since last long time. So this is something in brief. I will share his other things also to motivate our say participants. Say, as can be seen here is his list of publications, which shows a large list of general publications and very reputed journals like elsewhere, and a galaxy of journals. Say construction and building materials is a very reputed journal of elsewhere, and other very reputed journals, Journal of Cleaner Production. So as we can see that he is a man working in sustainability engineering since last time, sustainable development of SCC using waste materials and like this. So he has been working and guiding PhD thesis and the research. He has many research projects over the years. So rather, we are very fortunate that he is sparing time for this theme lecture. Uh, he has been very down to earth in interactions with us. Just to motivate our many of our young researchers, I am sharing his Google Scholar page, which shows that his I-10 index is very high, and as we can one can see that he has in recent years since 2016 his I-10 index is 42, which is extraordinarily high, and H index is very high. So this shows how much his work is being referred by the other researchers across the world and across the globe. So if one can note that he has done very good publication in sustainable technology and sustainable engineering, and with this
મારે શું આ તો પેલું થઈ જાય છે હું મારો અવાજ જતો રહેશે.
I request every participant to keep yourself muted. We will wait till Professor Sandeep Choudhary joins. And in the meantime, I welcome our senior professor at our department, Professor Dwivedi sir, also who has joined with us. So Professor Dwivedi sir, if you wish to say something to our dear participants, Professor Dwivedi sir. Professor A.K. Dwivedi sir. And as I have communicated to everybody that this session will be there till around 10:45 a.m. and then we will have a AICT common inauguration program which can be uh, mm, seen by the participants of the 72 FDPs starting today on YouTube. YouTube link has been shared with you all. So you are requested to join the common inauguration program of the AICT starting at 11 a.m. Then we have this our next technical session starting at 12 noon sharp. So I request you to join by 11:55 to 12 noon. So uh, that will be on geopolymer concrete, as Professor Mathur sir has already shared that Professor Saroj Mandalji from Jadavpur University is a very distinguished professor in the geopolymer concrete and other technologies. Professor Mandal sir will be sharing this knowledge, rich knowledge in the this geopolymer concrete. Then in the afternoon, 3:30 p.m. around from 3:20 p.m. we will start the session. Dr. Jitendra Yadavji from NIT Hamirpur will be the speaker. And I request everybody from you to kindly join in the morning in time so that we may get benefit and our sessions are not spilled over. As you can see, today the program is very tight, and all of you are sparing around 6.5 hours to 7 hours with us. So, any suggestion regarding this, may be shared on the WhatsApp group which has been created, as well as you may individually mail me if any suggestions will be there. So everybody may note that these sessions are being recorded, and every session will be recorded, and YouTube link will be provided, will be created, and YouTube links will be shared with the participants, and as well as shared with the AICT. I shall create the YouTube link as soon as possible, as soon as the recording is available with me, and share the YouTube link on the WhatsApp group so that you can see this. And every one of you knows this thing, that the system, WebEx system, records the time of login and logout of each of you. So from that system attendance, I shall be marking the attendance required by the AICTE, and I shall be submitting the same recorded by the WebEx system to the AICTE. And if you people are interested, because I plan to have some polls from tomorrow onwards during the session, as is prevalent in every AICT program. Those of you who have been attending those programs knows that AICT does polls to know who is attending at that time or who is not attending. Many times participants put on their laptop or the mobile and are not attentive. So to check their attentiveness, many times polls in between the sessions are used. So this will be also in place from tomorrow. Today is first day, so maybe today afternoon also we may have this. So Professor Dwivedi sir, if you wish to bless the participants, Professor A.K. Dwivedi sir.
I hope I am audible now.
Choudhary sir, namaskar. Good morning.
Namaskar.
Yes,
Good
you
morning.
are audible. So I welcome Professor Choudhary sir. And sir, your profile has been shared already with the participants, and we are very
Okay.
fortunate that you have spared time for us. And Mathur sir, आप कुछ बोलना चाहेंगे?
गुड मॉर्निंग संदीप जी.
Good morning. Good morning.
कैसे हो आप?
बस बढ़िया, first class.
Yes, I welcome you in our
Yeah.
this 1 week FDP program on sustainable engineering. And I know you are alumni of MBM Engineering College, Jodhpur.
बिल्कुल सर.
I am also from MBM Engineering College.
हाँ हाँ, आपसे तो मुलाकात भी हुई है पहले.
हाँ बिल्कुल बिल्कुल. And
बिल्कुल.
Praveen ji is from MNIT. You also served at MNIT. So we welcome you in our university. And probably when Corona will be over, we'll meet personally in some or other program at Kota. So welcome, Choudhary sir.
Sure, sir. बिल्कुल.
So I request our
Thank you.
keynote speaker, Professor Choudhary sir from IIT Indore, to start his theme session. Professor Choudhary sir.
Yeah, thank you, Agrawal sir, for giving me this opportunity, and again to interact with Mathur sir also. It's always nice to meet our alumni and our seniors. And I'll be discussing about this use of materials, and I have divided the presentation in two parts basically. The screen is visible? Just
yes, sir.
Okay.
Yes, sir. Screen is coming.
The screen is visible? Yeah.
It is white screen at present. It may come in a few seconds. It is white screen presently.
Yeah.
Still, it is totally white screen.
Presentation
सर अभी भी वाइट ही है सर इसमें. I think your voice is breaking. Might be some issue with the network. You may kindly try again, sir. It is white screen. The contents.
एक मिनट,
Yes, please.
just
These are the hiccups. Anyway, our participants are also joining in thin numbers in the morning, so they are uh, coming in sluggish speed, so that's why they are not missing. Anyway, so this kind of hiccups may be over in due course of time. So those participants who have just joined and missed the profile of Professor Sandeep Choudhary, our first speaker of the FPP. I may share again that he is Professor Civil Engineering at IIT Indore. हाँ चौधरी सर अब आ गया सर, अब PPT विजिबल है. Now PPT is visible, Chaudhary sir. Yes sir. Yes sir. I hand over again to Chaudhary.
yeah. So materials, right?
चौधरी साहब आपकी आवाज कट रही है. चौधरी साहब आपकी आवाज कट रही है सर.
Next one, how do we discuss
चौधरी साहब आपकी आवाज नहीं आ रही है. प्रवीण जी
सर आवाज नहीं आ रही, मैं भी ये देख रहा हूँ.
एक बार
हेलो,
उनको
हाँ.
कॉल आपकी आवाज नहीं आ रही है संदीप जी।
चौधरी सर को होस्ट बनाऊं क्या?
होस्ट बनाने से फर्क नहीं पड़ेगा, प्रेजेंटेशन तो आ ही रहा है उनका ना।
हाँ हाँ
आवाज तो कोई नेटवर्क की प्रॉब्लम है जिसकी वजह से उनकी आवाज नहीं आ रही।
सर।
हाँ
हाँ,
अब आ
अब
रही
आ
है।
रही है आवाज?
हाँ, अब
हेलो।
क्लियर है सर, अब क्लियर है
हाँ
सर।
ठीक है, मैं नेटवर्क चेंज किया।
सर
ओके, बिल्कुल ठीक है, ठीक है। हाँ, आई होप द स्क्रीन इज ऑल्सो विजिबल नाउ।
यस सर।
The next about sustainability, and I have divided the presentation in two parts. In the first part, we'll be seeing an overview about the type of the construction used and the types of replacements which can be done. We'll be discussing very basic aspects, a sort of overview. And in the next part, we'll be discussing the details, because at times it happens that we are tempted by utilizing or for using some waste material, but without caring much about what's happening inside. And even if we care, we just test the mechanical properties, or at the most durability properties, little bit of durability properties. But actually, whenever we have to establish some material as a alternative material, then only mechanical properties and durability properties are not sufficient. We need to look into the microstructure aspects also, because whatever is happening at the physical level is manifestation of that part only. So in the second part, we'll be discussing about the microstructure and how these alternative materials they influence the microstructure of the concrete, and how that can be improved, or what are the techniques by which we can see what's happening at the level of microstructure. Yeah. So in the first presentation, we'll be discussing the need for incorporating the waste for development of sustainable construction materials, then different classifications in which waste, like we can use them as supplementary cementitious material, as aggregate, as reinforcing material. Then the potential as supplementary cementitious material, potential as aggregate, potential as reinforcing material, and potential as architectural material. Let's talk about this very need of using sustainable construction material, that when already there are materials which are available in the market and which are well established from the strength point of view, durability point of view, and which are in use for decades, then why do at all we need to look for the alternative materials or these so-called sustainable construction material? The reason is simple: it reduces the pressure on the natural sources, because if we use the sustainable construction material, then of course we are using them as a replacement of those aggregates which we are taking from the nature, from the environment, and which is creating a huge burden on our environment. And also the other aspect is also there, that when we are using these wastes, so we are putting them at their end of life, and we are utilizing them in a better manner, else we have to dump them, so that will again eat up the land space, or we have to burn them, that will again cause CO2 emission. So this disposal of waste is also a problem. So it gives us a twin advantage, that it reduces the pressure, not only reduces the pressure on the natural resources, but it gives an advantage of disposal, or rather a better disposal of wastes. So we can say that if we jot down the benefits of using waste in construction material, there is a consumption of accumulated waste material to the conventional non-sustainable materials, and they need no or very less treatment or transportation cost. That's also important. And therefore they provide twofold solution for sustainable development by consumption of waste and by reducing the demand of natural sources. Now, broadly, we can classify them as a supplementary cementitious material, as aggregate, as a reinforcing material, or as architectural material. Of course, there are many waste which have multiple uses. They can be used as simultaneously as supplementary cementitious material, as well as aggregate also. So it depends, like aggregate may have more than, or the waste material may have more than one uses, but broadly we divide them in 4 type of uses. Now, coming down to the first supplementary cementitious material, as the name suggests, we are looking as an alternative, or we are looking to supplement the cement, and the different waste which can be used as supplementary cementitious material are fly ash, and most of us know that this Portland pozzolana cement already contains fly ash. Then GGBS, ground granulated blast furnace slag, that can also be used as a replacement of cement or as an additive, another additive. We can use rice husk ash also. We can use silica fume, metakaolin, glass powder, and marble powder also. And as you were discussing that waste material may have multiple uses. So like this marble powder is, at times it is used as supplementary cementitious material. At times it is used as filler. At times it is used as alternative to the fine aggregate. On the right hand side, you are seeing the microstructure images of the cement, fly ash, slag, silica film. Of course, the condition is that the particle size should be more or less in the same range, because we are going to replace the cement, or we are going to use this waste material as a replacement of cement. And here you can see, of course, that the particles of fly ash, they're quite spherical in nature. That means they will provide us more surface area for the reaction, and that gives an indication that yes, we are going to have good strength. Of course, silica fume particles, they're very fine. So if you zoom out them more, they are rather more spherical even than fly ash particles, and they give more higher strength. Now coming down to the fly ash, so its composition and property depends on the type of coal or biofuel burned. There are 2 types of fly ash which are available. One is class F. This contains less than 7% lime, glassy silica and alumina, and it requires a cementing agent like Portland cement, quicklime, or hydrated lime mixed with water to react, and cementitious compounds. The another type of fly ash which is used is class C. It contains more than 20% lime, and mostly it is self-cementing. The applications are, it is used in pozzolana, Portland cement, and of course, most of us know that it's mandatory nowadays for the cement industries to use fly ash in the cement. That's why there was a time 2 decades back when we used to get, mostly in the market, we used to get OPC, ordinary Portland cement, but now we get PPC, pozzolana Portland cement. Then, of course, it is used in embankment, soil stabilization, flowable fill, asphalt, concrete, geopolymers, etc. So if you see the microstructure of coal-based fly ash, you can see it's looking quite spherical, and we have also already discussed the advantage of that. It can be used in soil stabilization, and of course, it is used in fly ash bricks also. Another supplementary cementitious material is ground granulated blast furnace slag, popularly known as GGBS. And it is obtained by quenching molten iron slag, which is a byproduct of iron and steel making. From a blast product that is then dried and ground into a fine powder. Now, the main components of this GGBS are calcium oxide, CaO, about 30 to 50%, SiO2, 28 to 38%, Al2O3, and MgO. And we know that typical cement also comprises of this calcium oxide, silica oxide, Al2O3, etc. Only difference is the composition is different, and the amount of CaO, SiO2, that is different. But mostly, if you talk about the major components which are present in an ordinary OPC cement, then more or less these are the components which are there in the OPC cement. Now, increasing the CaO content raises the slag plasticity and thus increases the compressive strength. So we can see if we are getting more calcium oxide in a GGBS, or if you're comparing 2 GGBS, that which one is better than one which will have more CaO content, that will increase higher, more compressive strength. The benefits of GGBS are it reduces the risk of damages caused by alkali silica reaction. It gives a higher resistance to chloride ingress, and it provides higher resistance to attacks by sulfate and other chemicals. So this is how in the microstructure GGBS looks like, and right hand side you are seeing a picture which is showing the origin of GGBS, that how it is produced in the blast furnace slag in the steel industry mostly. Another very upcoming supplementary cementitious material is rice husk ash, agriculture byproduct of burning obtained by burning husk under controlled time temperature condition, or sometimes uncontrolled temperature also below 800 degrees centigrade. What is important is that it's highly pozzolanic because it contains 85 to 90% amorphous silica. Along with that, it contains about 5% alumina. And it has a very large surface area, which results from the microsporous structure of ash particles. It has a huge application area such as filler, additive, abrasive agent, oil adsorbent, sweeping component, as a suspension agent also for port. The benefits are it reduces the risk of damage which are caused by alkali silica reaction. Those who have been working in the concrete technology, they know that for the durability, it's very important to have less and less alkali silica reaction. So it reduces the damages which are caused by alkali silica reaction. It provides a higher resistance to chloride ingress, and it provides higher resistance to attacks by sulfate and other chemicals. So now, nowadays, in fact, this rice husk ash is available in form of, sometimes back 5 years, 10 years back, but this rice husk ash is available in form of bags, and there are manufacturers which supply this rice husk ash as any other material. This is microstructure of unground rice husk ash on left hand side, and on right hand side you are seeing the microstructure of ground rice husk ash. Of course, as the particle is this surface area of this ground rice husk ash is more, so we do expect higher compressive strength, or we do expect reactions in this ground rice husk ash. Another important supplementary cementitious material is silica fume, and it's an ultra fine powder which is collected as a byproduct of the silicon and ferrosilicon alloy production. Its spherical particles are less than 1 micrometer in diameter. So important is it is approximately 100 times smaller than the average cement particle. So the lower size means we'll get a higher surface area, and the higher surface area means we'll get more reactions. So because of this lower size and because of particularly the spherical shape, so its size and shape both are helping out in a good reaction and in achieving a higher strength. In fact, this is the material which is used when we need to go for high strength concrete or ultra high strength concrete, because when other materials come to their limitation, and then if you use silica fume, it definitely gives you a high strength. And by using silica fume, you can definitely reach up to AM80 even in the normal laboratories. And its high fineness and the presence of SiO2, which is there between 85 to 98.5%, is responsible for highly pozzolanic reactivity. So there's a high fineness, there's a higher SiO2, and the oxides of silica fume, they react with and consume calcium hydroxide, and that is CH obtained from the hydration of cement. So this calcium hydroxide, which is there and which we get there after the hydration of cement, with silica fume, it's consumed. The benefits are it densifies the matrix, it improves the strength, it decreases the porosity, and it gives a better resistance to chemical attack. I hope I am audible and there's no
Yes, sir.
issue in screen
There,
sharing.
there's no issue in
Yeah,
the
okay.
voice now. Also, there's no issue.
Okay. Okay. So now if you see the microstructure of silica fume, you can see that the magnification level is too high. 1 micrometer on the right hand side is 300 nanometer, and you can see very spherical particles even at this magnification level. So that instills or that gives a confidence that yes, it will give us higher strength. because of higher surface area which is available for the reaction. Another recently popular and the other material on which people have started working, and which is in fact the future of cement industry, is also kaolin. It's produced by calcination of high purity kaolinite clay mineral at a temperature range of about 700 to 850 degrees centigrade. It is finer than cement particles and it helps to fill the micropores of binder. It contains high amount of reactive silica and alumina. It provides better particle packing and a greater pozzolanic reaction rate. Benefit: it improves the compressive strength at early ages. It leads to low permeability and it decreases the chloride ion penetration. And we know that this chloride ion penetration is a big nuisance in terms of the durability of concrete. So ideally, the concrete should have zero chloride ion penetration, but anyway, there's always certain chloride ion penetration, so that should be minimum. So it helps us in that. And this is a typical microstructure of metakaolin. People are now working on this LC3 cement also, which this metakaolin is a major component. And in many countries already this cement manufacturing using metakaolin has started. It's a matter of time, and soon we'll also be getting LC3 cement. Another supplementary cementitious material is glass powder, and there's a it also has a pozzolanic activity, and if increase its fineness, that increases the pozzolanic properties further. There's a high amount of amorphous silica and high specific surface area. So this amorphous silica and high specific surface area, this gives us or this contributes for pozzolanic reaction. And there's less water absorption and smooth surface, which reduces the water and admixture demand. Now, this alkali silica reaction occurs among the silica of glass and alkali and cement, alkali which is present in cement, and leads to expansion, internal stress, and crack formation with disruptive effect. So, thus, this use of high proportion of glass particles is limited because, as we were discussing earlier, alkali silica reaction is basically detrimental to the durability of the concrete. Powder is a sustainable material, but it is causing alkali silica reaction. So we cannot use this for a very high replacement level. So we have to properly calibrate, or we have to properly find out the optimum dose up till which this alkali silica reaction resulting from the use of glass powder does not affect the durability of the concrete. The benefits of the glass powder are it improves the workability, and it decreases the permeability. Most important parameter which defines the durability of the concrete is permeability, and if it is decreasing the permeability, then we can safely say that it is increasing the durability of the concrete, and also it improves the resistance to chloride ion penetration. Next supplementary cementitious material is marble powder. So it's basically inert or quasi inert material, filler for some time, but later on people realize that it can have certain cementitious properties also. It can be used as supplementary cementitious material also. So the calcite and Portland cement pastes lead to calcium carboaluminates, which are formed by a reaction between hydrated calcium aluminate and carbonate ions. And this calcareous filler has an important binding property, which is developed by hydration of calcite and C3A. And strength improvement at lower replacement level can be observed mainly due to the filler effect. Replacement level, they cause delay in setting time and lower the strength. The benefits are it increases the compressive strength, abrasion resistance, and sodium sulfate resistance. So this is, we know that there's a huge amount of marble stone dust, and the industry is finding out quite difficult to dispose it safely. So there's ample scope of research, ample scope of development of technology in this aspect. If somebody can come up with the optimized doses of marble powder as a supplementary cementitious material or even as a filler for the construction industry, then it will be readily taken up not only by the construction industry, but also by the stone processing industry, because they also face a lot of heat from the enforcing authorities because they're not able to dispose of this waste properly. So it carries a ample amount of scope. Now, this we are discussing about the waste utilization of waste as a supplementary cementitious material, but they can be used as aggregates also. And I have picked certain waste which can start, but we'll be discussing about 4 or 5 important waste which can be used as aggregate, like scrap tire rubber particles, waste plastic aggregates, construction and demolition waste, copper slag, marble or Kota slurry, and cenospheres. Now, scrap tire rubber particles, crumb rubber particles, or ground rubber particles. Now, rubber aggregates they are obtained by mechanical grinding at ambient temperature or cryogenic temperature, and then they are separated into different sizes. Now, we can use chipped rubber as coarse aggregate and crumb and ground rubber as fine aggregate. So it has multiple uses depending on the size in which we extract the rubber particles. They have multiple uses. It has a low modulus of elasticity and ductility of the material. So that is the USP of this material, that it has having low modulus of elasticity, and this flexibility is giving us higher toughness and ductility. And also it has low specific gravity. So this helps basically in developing lightweight aggregate cementitious particle. The hydrophobic nature of rubber particles restrict the ingress of water and other solutions, which affect the properties of cementitious material. Ground, crumb, and chipped rubber aggregates. The idea behind discussing this at the top is that this is the waste material, which is available globally and which is a nuisance globally across the world. There might be other waste materials also, but their presence or their nuisance is limited to a certain extent. But this is there across the world in each major city, small city of the world, everywhere this is the problem. And the problem is same, disposal of waste rubber tires. So people have started thinking in this direction, and they've used now also building products also as ground in the ground manner, crumb rubber or chipped rubber size. Similarly, there are waste plastic aggregates, and different forms of plastic waste have been used as aggregate, filler, or fiber in preparation of cement, mortar, concrete after mechanical treatment. And the sources there are waste plastic bags, this PET bottle, then the PVC pipes, then HDPE, thermosetting plastics, mixed plastic waste, etc. All of them are a nuisance and their disposal is a problem. And we have to look for certain solutions for these type of waste. They are basically strong, lightweight, and durable composites. And if we use them in building materials, they reduce the weight density of the product or structure. The benefits are the increased toughness, flexural strength, abrasion resistance. They increase the chemical durability and shrinkage resistance. So they have certain benefits. Of course, there are certain disadvantages also, and the major disadvantages are they create a impermeable layer, or they don't allow the proper bonding of the aggregate and cement paste many a times. So there's a obvious reduction in the strength. But we know as a civil engineer that many times only strength is not the parameter. we might go with a lower strength where higher strength is not required. There are many applications where only minimum strength is required. Everywhere we don't need to go for high strength concrete. And in those cases, we can look for this waste plastic aggregate because its other advantages. So these are like waste plastic aggregate concrete, which was in one of the research projects we developed. So you can see the plastic which has been used here, and this is how we shredded the waste plastic bags through a hopper. Then this C&D waste also, this construction waste includes materials such as insulation, nails, electric wiring, shingles, and roofing, as well as waste originating from site preparation such as dredging materials, tree stumps, and rubber. Waste is a waste debris from destruction of buildings, road bridges, or other structures. So again, this construction waste and demolition waste that can be used in the buildings as a sustainable materials. We can take out whatever is useful for us. And again, people have started working on this. In some cities, they are making the paver blocks and bricks using this C&D waste. So applications, if we talk about the recycled coarse aggregates can be used. So there can be recovery of coarse aggregates from demolished concrete, and they have the enough ability to produce good quality concrete. Then construction debris, they can be used as fine aggregates, and small efforts are required for processing construction debris as fine aggregate. And it has certain applications like in manufacturing of unfired bricks, mortar, paver blocks, etc. Then embankment material, this can be used for improving soil bearing capacity, embankment, plinth filling, etc. Then ceramic waste aggregate like waste wall tiles, floor tiles, sanitary ware, household ceramics, and technical ceramics. In recycled timber, again, wood can be reused, repurposed, recycled, or burned as bioenergy. Repurposed or recycled wood can be used in pathways, coverings, mulches, compost, animal bedding, or particle board. Another important waste material perspective, particularly copper slag, and it's an industrial byproduct which is obtained during the smelting and refining of copper. And its texture is black colored glassy. It contains silica oxide plus Al2O plus Fe2O3, which is in total more than 70% of the composition. And its use in cementitious material has shown pozzolanic properties. And use of copper slag as fine aggregates increases compressive and tensile strength of concrete, and it decreases the water absorption and depth of carbon penetration. So again, people have worked on that, and still people are working on finding out the optimum doses. This is a microstructure, and these you can say huge dumps of copper slag, which are there. Another material is cenosphere. This is produced as a byproduct of coal combustion at thermal power plants. And there are hollow microspheres of size 5 to 500 micrometer, having shell thickness 5 to 10% of the diameter. And they contain about 50 to 60% amorphous silica. And why we are saying again and again amorphous silica is because we know that it's not the total amount of silica is not important, SiO2. What is important is its presence in amorphous form, only then it will contribute to the reactions. Then 20 to 30% of Al2O3, 1 to 8% of Fe2O3. And it includes calcium, magnesium, phosphates, chlorides, and sulfate. So basically, they're lightweight, inert, hollow sphere, and they have the resistance to thermal and electrical conductivity and superior acoustic properties and beneficial for developing lightweight cement composites. Lightweight cement-based composites with density in the range of 1120 to 1920 kg per meter cube can be obtained. So this is a typical microstructure, and they can be used as a fine aggregate. So again, if you are seeing the microstructure as we have been discussing earlier, they're quite spherical in the shape, and this spherical shape gives us a large amount of surface area. and which of course will lead to higher reactions and which will cause to more strength. This can also be used as reinforcing materials like scrap tire rubber fibers. They can be used as reinforcing material, not as alternative to the steel reinforcement, but arresting the shrinkage cracks or arresting other cracks. Recycled steel fibers, waste plastic fibers. Again, as a caution, we should understand that when we are using these fibers as a reinforcing material, then these reinforcement doesn't mean that we are going to replace the steel reinforcement. A steel reinforcement has different purpose, and steel reinforcement improves the flexural strength of the structural component, whereas these reinforcements, they don't improve. They might improve, but we should not use them for improving the flexural strength of the member. And this is a mistake which many times people do when they use fibers in the concrete. They try to look for improvement in the flexural strength. It may improve the flexural strength, but its primary purpose is to arrest the cracks. And then, of course, you can use recycled glass or carbon fiber reinforced polymers and natural fibers. So scrap tire rubber fibers, if we talk about them, then they are chipped or crumb tire rubber particles in fiber-like shape. We'll be seeing them in some slides. They have a flexible nature, which helps for better workability. And they increase shrinkage resistance, of course, because of their length and crack arresting property. And they provide better post-failure performance as fiber particles help to bridge the cracks. They increase in flexural strength, but that's not our primary motive when we are using the rubber fibers. And of course, they improve the impact resistance because of their ability to absorb the energy. And they also provide us a higher resistance to abrasion, chloride ion, and carbon penetration. And they're less affected by acid attack, which is measured in terms of mass loss and compressive strength loss. So this is the microstructure, and you can see the microstructure of a rubber fiber itself. And you can see in itself has certain cracks. So what happens, why it improves the ductility or impact resistance is whenever we provide energy, first these fibers, they will crack in themselves. So they will absorb the overall energy which will be taken up by other parts of concrete, that will be less. And this is how the rubber fiber, typical photograph of rubber fibers. We can use them for concrete. What we need to do is we can talk to those people who are using waste tires, like retrading persons or some other persons, and we can ask them. They can provide us, shred the tire, and they can provide us the fibers in different sizes. We can also use recycled steel fibers, and a scrap tire consists of around the rubber and 20% of steel fibers also, and 20% of textile fibers. So rubber fibers we can use, steel fibers also we can use. And processes are available for extraction of steel fibers like shredding, then cryogenic process, pyrolysis presses, and microwave-induced pyrolysis. Of course, pyrolysis is not a good process because here they burn the tire and then they take out, because steel will not burn, they take out the steel. So that's not a good process. But anyway, these are the processes with steel fibers. They have the good tensile strength, modulus of elasticity, and the specific gravity. All of them are like that of synthetic steel fibers. And they can improve the properties of different composites by considering and by using them with other fibers also. And this is how the recycled steel fibers look like, and this is the microstructure. Waste plastic fibers can all be taken out from waste plastic bags, PET bottles, PET bottles, the normal water bottles which you're using. Of course, the PET bottles can be used as reinforcing bars to the structural members up to a certain extent. And they're lightweight, high strength ratio, and durable. They increase the flexural strength.
चौधरी साहब आवाज थोड़ी चली गई, अभी तक आ रही थी, जस्ट इस स्लाइड में आवाज नहीं आ रही।
So your voice is breaking.
चौधरी साहब आपकी आवाज नहीं आ रही है।
Fibers.
हाँ अब आ रही है।
And these, yeah, hello.
हाँ अब आ रही है, आने
These
लगी।
glass fibers and carbon fiber reinforced cementitious materials have high compressive strength, tensile, flexural, and impact strength. And the use of virgin glass or carbon fibers in construction materials is, of course, expensive. However, we know that there is a significant amount of unfinished material which is left as a waste. Along with this, a large amount of FRP is also discarded at the end of service life. So it's not about using the virgin glass or carbon fiber, polymer fibers. We have to look for those waste material, even that will work for us. And the effective recovery of this glass or carbon fibers from waste FRP can provide similar properties that of virgin fibers. And it has been observed that when these recycled glass or carbon fibers were incorporated in the concrete, they improved the mechanical properties of the cementitious material. So this is how they look like, recycled glass fiber reinforced polymers and recycled carbon fiber reinforced polymers. So these are the photographs, and just along with the scale, you can see their sizes. We can also use natural fibers, and different forms of plastic waste have been used as aggregate pillar or fibers in cement mortar. Just stop it. So these are the natural fibers which can be used, like coir, coconut fibers, sisal fibers, oil palm fibers. So of course they have been used successfully for improving some properties of the concrete. Of course, since they are organic material, so we need to look into detail into the durability aspects. What will be the overall effect with time of the climatic actions or extreme weather conditions on this? That is an area which needs to be worked upon. But still, we can think of using these coconut fibers, sisal fibers, or oil palm fibers. And then, of course, some waste they can be used as architectural material also, like I'm just sharing what people have done. So like they made a sort of hut by using this bottles, by using bifusion bricks, by using recycled cardboard bales. So this gives us a confidence that we can also look for some waste material which is available in our nearby vicinity. And we can also think of such innovative ideas, and we can also use them in construction. So, and like this insulation material, which is made primarily from discarded glass and additional natural raw material. Then agricultural waste panels made from compacted agriculture byproducts such as rice husk, groundnut shells, wheat husk, barley husk, corn stalks, or corn husk. Then insulation bats made out of natural cotton fibers obtained from disposed jeans and denim fabrics. So the idea is idea to show these two slides is that the sky is the limit, and it's not just there are not only text. It's not that there are textbook solutions only. There are thousands of the applications, and we can think out of the box also. There's so much waste material available around us, which has no use as such, and whose disposal is also a problem. And if we can really come up with some solution, then that can be a wonderful contribution to the society. So that was the first part. Just a minute, one more. Yeah, then it has been used like as a tough roof also, like from tough roof made from Tetra Pak cartons or a combination of paper, polythene, and aluminum. Then GR green slate made out of polythene milk bottles and plastic bags into roofing tiles. Then bioglass made of 100% discarded glass material without any addition, colorants, or additives. So different uses. Then finishing products, right? Repeatera, Troco sheets, wine cork tiles like Repeatera. This is made from natural stone lookalike plates, but they are created entirely from polythene derived from municipal solid waste and wood which has been collected from industrial processing. Then this Rocco sheet, it is produced out of paper waste. These wine cork tiles, they are produced from whole cork stoppers. And so different types of products can be used. So this was the first part of the presentation where basically we have discussed and we have seen the overview of different applications of the waste materials. And now let me come to the second part where we'll be seeing, just a minute. I think that sharing has been stopped. Agrawal sir?
That sharing has been stopped. I think you are trying to share another slide.
Okay. Yeah. Now this is visible?
Yet not. Yes, yeah. Now it has come, sir.
Okay, just so in the first part we are discussing about general concepts of the use of waste materials for sustainable construction. And as I discussed in the beginning, that it's not only about just using 10%, 15% and just replacing and then saying, okay, we have used, we have replaced. We need to look for three different aspects whenever we are replacing any material. And those three different aspects broadly are the mechanical properties, second is the durability properties, and third is the microstructure. I'm skipping the first two parts because I know I understand that at this level most of us are acquainted with the mechanical properties and the durability properties. So I'm straight away jumping to the third part, that's the microstructural properties and microstructural techniques to see how the things are happening. So that whenever we are using any waste material and we are thinking about that, we do implement these techniques and then we can see how much they are affecting finally the physical properties, that is the mechanical properties and durability properties. And of course, as I have told earlier, that those mechanical properties and durability properties, they're basically a manifestation of this microstructure only. So before going to the microstructure, we have to understand the complexities of the concrete, and many times it so happens everybody is trying to work in the concrete and they think that it's a simple mix of just cement, coarse aggregate and fine aggregate, and little bit of water is to be added. But that's not sufficient. There's a lot of complexity which is actually involved in this cement chemistry and of course then later on in the concrete. So even if you see a chemical composition of cement, typically then it comprises of C3S, elite, which is responsible for the early strength. Many of us know that. Then it is there's a C2S belite, there's aluminate C3A, there's a ferrite C4AF, there's gypsum CS, and there's a Portlandite CH. So even and these are not the final or the complete list of the elements which are there in the cement. There's a whole bigger list, but these are the major components. Why we're discussing that? That means the things are not that simple as it looks over the surface. And if you see the chemical reactions of the cement, here I have listed certain reactions, and you can see so many reactions are taking place at a time. So it's just not that one single reaction is taking place. There are so many different types of reactions which are taking place. So many chemical activities are taking place when there's a hydration of the cement. So it's very important to understand the role of cement chemistry also, because on the durability. And we know that, yeah, am I audible?
Yes, sir. Yes, sir.
Yeah. So the durability characteristics also, like carbonation, acid attack, chlorination, they depend on the free lime which is present after the cement hydration. Similarly, water penetration depth depends on the pores formed from volume reduction. Similarly, alkali silica reaction, sulfate attack, effect of seawater, and other environmental threats can also be better understood by cement chemistry. And this cement chemistry as such can be understood in turn by the microstructure analysis. So what is this microstructure analysis all about? This is basically done in two phases. One is typical microstructure analysis, where we identify the mineral arrangement under the microscope. And here we do it by using scanning electron microscopy, optical microscopy, and then TEM, etc. On the other side, we also need to do the chemical analysis, where we identify the types of mineral which are formed in the concrete. And of course, we can study them using EDS, XRD, spectroscopy, etc. Now, this is a typical microstructure image of concrete, and it's quite interesting that on the left hand side there's a bigger image, and this is what you see with naked eyes, and this is what we think concrete comprises of. But if we zoom it out at 200 magnification level, it will look like this. If further zoom it out 2000x level, it will look like this fibers. If you further zoom it out at 5000 magnification level, it will look like this. So why we are discussing this is because it's not what is being seen by the naked eyes. There are many other things which are there, which we have to study if we really want to see what is the strength, if we really want to understand the overall concrete. So, and if you see this scanning microscopy, then typically what happens is there's an aggregate, then there's a transition zone between the aggregate and the cement paste. So always there will be a zone which is lying between the cement paste and aggregate. And that zone is also very important. That's called transition zone, and at times that's called interfacial transition zone also. So this is a typical microstructure of concrete, how it looks like. So you can see aggregate, and then you can see the cement paste here. So this is the aggregate, this is the cement paste here, and this is the transition zone which is lying between the cement paste and aggregate. This transition zone is very important. Normally we don't talk it about when we talk about the mechanical properties. We talk about the strength of cement, we talk about the strength of aggregate in itself. But actually, if you talk about the strength of the concrete, then that is mostly governed by this ITZ transition zone or interfacial transition zone, because this is the weakest portion or weakest link in the concrete, which will define the strength of the concrete. This is how a hydrated cement paste looks like. So typically you can see here A is CH, this is showing calcium hydroxide. And then this B part is showing CSH, calcium silicate hydrates, and C are ettringite needles. Now calcium silicate hydrate, or rather this B part, it comprises 50 to 60% of the solid volume in hydrated cement paste. Ideally, we should have more and more amount of hydrated cement paste in concrete. And Then this calcium hydroxide crystals, they contribute 20 to 25% of the solid volume, and remainder is occupied by this attringite needles and all other aspects. What is important is that even if we see this scanning microscopy, electron microscopy, and if we are comparing two concrete samples, and if you are seeing in one this B part is more, that calcium silicate hydrate is more, then we do expect a higher strength for that. So that means this microstructure can give us indication about the strength and other aspects, because this ultimately this calcium silicate hydrate, this is going to provide the strength. And if you ask our choice in which this they should be present, then the highest amount should be of calcium silicate hydrate, next amount of calcium hydroxide, and then next is about attringite and all other aspects. We can also see incompletely hydrated cement particles, and they are easily identified by their characteristic brightness in the image. So, and they have a tendency to attract each other and form flocks. And this is how a paste aggregate interface looks like. So this is the aggregate, this is the paste. So normally this is the weakest zone, and whenever we are using some alternative materials, then what we can do is we can see the paste aggregate interface of concrete when the alternative material is not used, and then the paste aggregate interface of concrete when the alternative material is used, and then we can see the properties of this aggregate interface, and the one which has better paste aggregate interface, better bonding, will give us more strength. This is why the microstructure study of concrete becomes quite important and quite complex. We have to see not only the interparticle spacing between calcium silicate hydrate sheets, but we have to see the entrapped air voids also, which are present there in the concrete. So why it is important is the size of these interparticle spacing between CSS sheets is about 1 nanometer, and the size of entrapped air void is about 1 to 10 mm. So we have to magnify in such a manner at so many magnifications levels that not only we are able to see at 1 nanometer level, but we are able to see at 1 millimeter level also. And why that is important, if we compare them with respect to sizes, then if this interparticle spacing between sheets is represented by size of human being, then this entrapped air void is represented by size of about, say, Mars. So as consider that you have to do a study where there's a person standing there, and you have to write down about that person also, and then you have to write down at different types of activities in the environment, and then you have to go up to the Mars and you have to write down a statement about Mars by seeing that Mars at zooming by magnifying something, and then you have to correlate that human being with the Mars. So these are the issues which are there in the microstructure of concrete. So one needs to be very expert, and when we needs to do a lot of microscopy to understand all these things. Coming to, like, we were discussing about mineral admixtures, like we can use different waste material as mineral admixture. So here we can see that whenever we are using mineral admixtures, like here silica fume, this is low silica fume, low water cement silica fume concrete. And here we are seeing that when we use silica fume, we are getting quite dense hydrated cement paste. So this is now telling us, we were expecting there that when we will be using silica fumes, the surface area will be more, that will cause more reactions, that will give us a higher strength. Now this microstructure is validating that. It is telling us that yes, there's a large amount of hydrated silica paste, CSS gel, hydrated uh, cement paste. So this is what we can observe by using this. Again, very interesting, like here we try to use, this is our laboratory study, we try to use rubber ash, waste rubber ash in concrete, and then we try to see what's happening at the interface level, which is the weakest part. So this is the rubber ash particle, and this is like sort of aggregate, and this is a clearly visible gap between the aggregate and the rubber ash particle. So that means that yes, not aggregate, basically this is cement paste, sorry. So there's a clearly visible gap between rubber ash particle and cement paste. That means that this interface is not good, and that means we will be getting lower strength. Here, like this rubber ash particle, we can even see the crack within the rubber ash particle also. So it also gives us a lot of information that how the durability properties will be affected, how the mechanical properties will be affected due to this crack in the rubber ash particle. So here you can see the cracks, gap. So here you can see this cement paste gap. This is the rubber fiber. Here we try to use the rubber fiber. There's a crack within rubber fiber. There's a cement gap between the cement paste and rubber fiber, and how this crack will be affecting the properties at the mechanical level, that that can be studied. Again, here clearly visible gap between cement paste and rubber fiber. That means when we are using rubber fiber in concrete, then our interface is not going to be that good, and so we do expect some decrement in the strength. So like here again, this is a clearly visible gap. So you can see here it's a hybrid concrete. So there's a gap between this cement paste and rubber ash particle this side, and cement paste and rubber fiber particles this side. Clearly visible gap between these. And again, more clear, this is the rubber fiber, and this is a hybrid concrete which comprises rubber fiber and rubber ash. So this is the aggregate, this is the rubber fiber, and these are the ash particles lodged in interfacial transition zone. So this is the interfacial transition zone, and the rubber ash particles are lodged in this interfacial transition zone. This is the internal cracking of fiber. The fiber is cracking internally, and these are internal micro cracks on the rubber fiber. So again, here you can see the aggregate. This is the aggregate cement paste, and these are the rubber ash particles which are lost between them. The lost rubber ash particles and IITZ, micro cracks in rubber fiber. Again, what do micro cracks mean? They mean a lot. That if the cracks were not initially there and the cracks have developed later on, that means during the impact, that means the rubber fibers cracked due to the impact, and that means a major part of the energy that was absorbed by the rubber fibers. So different types of interpretations can be done by going through these microstructure images. So what is important is we need to understand that yes, we need to do this we need to go through these microstructure images, and then that can give us a lot of information. Like you can see when we did another study on the temperature also, here you can see the rubber fiber, and there's initially some gap between the rubber fiber and cement paste, and then we increase the temperature, so the gap between the rubber fiber and cement paste is increasing. Further increase the temperature to 600 degrees centigrade, the gap is increasing further. And so, and what is important is that there were cracks in rubber fiber at normal temperature also. That means during the cracking, during higher temperatures, this crack will also play a certain role. And at 600 degrees centigrade, this crack, which was initially of this size, this crack has become more. So the crack which was there within the rubber fiber, that has also opened up at higher temperatures. And here you can see a clear cut gap between the rubber fiber and the other parts of the concrete when the temperature is up to 750 degrees centigrade. And you can see surface cracks also in the microstructure through microstructure image. Another type of study which can be done through microstructure is like if you are seeing the cement particles, they are looking like this. Important is we have to compare the two particles or two types of materials at the same magnification level. So if we are seeing at 30 micrometer level, or this, rather you can see this magnification level of 2500x. Cement particles look like this, fly ash particles look like this. That gives us a direct indication that fly ash particles are more smooth, more spherical, and they will give better results. Like if we try to replace the granite waste, fine aggregate by the granite waste also. So you can see we can do some microstructure images, and we can see how they will work upon. So like when we use the granite waste, another type of stone waste in the concrete, Then we can see what is its effect on interfacial transition zone. So the idea is just to give an indication, to give a flare that different type of microstructure images can be captured, and those microstructure images you can capture the interfacial transition zone, you can capture the voids, you can capture the cracks, and then you have to do your own inferences, and you have to do your own calculations. You have to develop your own theories that how they will be affecting the final properties of the concrete. Like this silica fume particles under TAM has a much higher magnification level. So this is denoting 0.5 micrometer only. So again, they are quite smooth and spherical. So that is telling us that yes, if they are quite smooth and spherical, we are going to expect a good strength. That was about mineralogical arrangement, and then we can see mineralogical composition also. And for that, one of the important tools and most popular tool is X-ray diffraction. And that's based on a simple concept that each crystal has a unique pattern and it reflects different intensity of light at different angles. And XRD analysis can identify the minerals which are present in the sample using these observed intensity patterns. So we can those people who are from the chemistry background, they do a lot of XRD, X-ray diffractometer. So in our institutes, mostly we do have the chemistry departments, universities particularly, and mostly they do have this XRD equipment. So we can take help of them and we can do XRD analysis of our material also, concrete also. So at what angle, which mineral or which compound will be reflected back? For that, there is a standard database which is available in the literature. So like say typically calcite, that will be deflected at these angles, 3, 1.8, 3.8. And so different angles are given at which they will be deflected. And out for those angles, if we are seeing something is getting deflected at a particular angle, then by reverse engineering, we can find out what can be the mineral which is present there. So like this is a typical XRD pattern of alite. So you can see the angle at which we are seeing a peak is somewhere between 51 to 52 degree. So it's a rhombohedral single sharp peak. It's monoclinic, two sharp peaks. So the angle is like between 51 to 52 degree. We are seeing halite, and different component, other symbiote composites can be obtained like C2S belite. It has its different angle. Belite, you are seeing mostly it is between 30 to 31 or at these angles. And halite was 53 to 54. So different ranges. So like this is XRD for fly ash, which we did in laboratory. And we could easily identify that it has mainly quartz and mullite in itself. So the different peaks of quartz and mullite, which we got in XRD. And when we tried to replace fine aggregate by granite waste. So first we did this XRD of fine aggregates, and fine aggregate we are seeing we are obtaining quartz, albite, microcline. Whereas in granite waste, along with quartz, albite, microcline, we are getting orthoclase and orthoclase also. So that means that if you are using granite waste as a replacement of fine aggregate, then there are two another compounds which will be there, orthoclase and anorthoclase, and then we have to see what will be their effect on overall properties of the concrete. So this is how we can predict and we can infer what's going to happen when we are going to replace the conventional materials by these sustainable materials. Like another typical example of use of this XRD technique, like we try to use ceramic waste as a replacement of fine aggregate in concrete. Then we did a XRD analysis of traditional concrete, and then a concrete which consisted of 40% ceramic waste, or ceramic waste for 40% replacement of fine aggregate. So in traditional concrete, we got in the end silica, CSH, portlandite, atrazite, etc. And in the concrete containing 40% ceramic waste, more or less we got the same minerals. So why it is important is that overall actually it has no major effect on the mineralogical composition of the concrete if we are using ceramic waste. So that means we don't expect any major change as such any adverse effect as such on this concrete when we are using ceramic waste. So like we can compare different ceramic waste using this. We can use this technique for alkali silica reaction also, for identifying the sulfate minerals also, because many times it happens, people think that sulfate mineral means only one type of sulfate mineral, but that is present in different forms like adringite, thomsite, calcium monosulfate hydrate, gypsum, bohemite. And what is important is adringite has a different role to play, thomsite has another different role to play, then calcium monosulfate hydrate has another role to play, gypsum has another role to play, and bohemite has another role to play. So traditionally we think that we just need to find out that this is the amount of sulfate minerals which is present, but that's only one half of the story. What is important is in which form the sulfate is present. That will decide many things. Then we can go for IR spectroscopy also. So this is based on the wave absorption, energy absorption, and this tells us about the type of bond which is present there, and then we can see the bond is linked to which mineral and the strength of that bond. So this IR spectroscopy can also be used, and we can identify different functional groups. Like here gypsum has been identified, here dolomite component has been identified. So like at different wave numbers will find out different, like C3s, even C3s can be observed at different wave numbers. So it's not just important that I have allied C3s in my cement and that's it. That's all. No. What is the phase in which it is present? Is it present in triclinic phase? Is it present in monoclinic phase? Or is it present in oxidizing phase? Because that will also again tell that how much reaction has taken place, and how much how much is the strength which we finally do expect from C3s, because there might be one C3s with having more triclinic and less oxidizing, and another with more oxidizing, less triclinic phase. So that will carry a lot of meaning. It's not just total amount of C3s. Same is for C2s, like in which form it is present, beta C2s, oxidizing or reducing, then C3a in cubic, ortho, or C4AF or quartz, whatever. So we have to identify these cement composites, and so we need to understand like there's a considerable difference between the spectra of monosulfate, like adringite, etc., and various forms of calcium sulfate can be clearly identified by IR spectroscopy. We can do FTIR also, like through FTIR we can obtain the functional bonds, and we can find out to which mineral they are assigned, and then that gives us the strength of concrete. So another important technique is NMR. NMR spectroscopy is being used, or has been used rather, by chemistry persons for decades, hundreds of the years. But recently, people have started using it for our construction industry also, concrete technology also. And through NMR spectroscopy, I'll not go much in detail here because our primary purpose is something else. But what happens is through NMR spectroscopy, actually, like we can identify the degree of hydration. So like here, two types of concrete are compared. In the first type of concrete, the degree of hydration is 48%. In the second type of concrete, we got the degree of hydration 73.4%. Now this we cannot get directly from these mechanical properties and durability properties. Now, if we know that in one cement the hydration is only 48%, in one concrete the hydration is only 48%, in another concrete hydration is 73.4%, then it is quite obvious that the concrete in which the hydration is more, that will give us more strength, that's better concrete. Then there's a bond chain length, and so the bonds which are formed, what is their chain length? If the chain length of the bond is more, then naturally that concrete will be better, that will be more strong. So the chain length is 4.13 only in, say, the first type of concrete. In the second type of concrete, it is 4.21. So that again, we can find out through this. And there's another term which is written here, Q1 by Q2, if you see here. So Q1 by Q2 in the first traditional concrete, say it is 0.934, and in the other concrete is 0.903. So this Q1, Q2, etc., there are different phases. So action has taken place. So ideally, if Q2 will be more, then Q1 by Q2 will be less. So lesser value of Q1 by Q2 will mean that concrete is better, more hydration reactions have taken place, advanced stage of reaction has reached. So we can see see the strength of this technique. We can find out that which phase of reaction has taken place, what is the stage at which the reaction is there, what is the degree of hydration overall, what is the bond chain length. So if you are using some alternative material, then we can use that alternative material. We can cast the concrete and we can do NMR spectroscopy. And through NMR spectroscopy, we can easily find out. Like here, we are quite confident that when we are using 40% ceramic waste as a replacement of fine aggregate, not only we are getting more reaction, more degree of hydration, but a higher bond chain length also. Then it's quite obvious I'll get all the properties better. And it also happened when we tested for mechanical properties and durability properties. Everything was better than the traditional concrete. Another very recent technique, just to give a glimpse. Of course, it's not for day-to-day use, but as a civil engineer, we should be aware that there are very high-end, very sophisticated techniques which are available when we are using certain waste material to instill a confidence among us, and that's lateral force microscopy. So here, basically, there's a sort of tip and which is moving across the surface of the concrete, and it is tapping the surface of the concrete at very regular interval. It's very, very fine tip. It's mostly used for metals only, quite costly equipment. But once it goes through this concrete surface, then it makes a profile of the concrete surface. If the profile of concrete surface is smoother, then that means when we use the waste material that has resulted in better properties. If it is not that smooth, that means the properties are not better. So this is the surface topography with roughness profile. So here on the left hand side, you are seeing traditional concrete. On right hand side, you are seeing concrete which consists of 40% ceramic waste. So it is showing us unhydrated cement particles in the traditional concrete, which are not visible in 40% ceramic waste concrete. And it is showing us a lot of pores also, which are not there in 40% ceramic waste concrete. So that again instills a confidence that yes, when we are using this waste material, we'll get less number of hydrated cement particles and less number of pores. We can also do this 2D and 3D phase imaging. So in this traditional concrete, you are seeing non-homogeneous phase. And whereas when you use this 40% ceramic waste, we got more or less a quite homogeneous phase. And when we do 3D imaging, we see higher variation in distribution of phases in traditional concrete. But when you use a waste material, we got relatively smooth distribution of phases. So this is a complete sort of sequence or complete protocol of different microstructure techniques which we need to do if we really want to establish some waste material as a replacement of fine aggregate or cement or coarse aggregate, whatever in the concrete. So these techniques, they can resolve the durability issues, they can determine parameters that influence the reaction kinetics, and they can be very helpful in developing and characterizing new materials for durable structures. And they are also helpful in establishing the reasons for structural failures and conducting related forensic investigations. And they can provide a basis for development of relevant standards and methods for advancing aspects of objective-based codes and for establishing and for putting clauses for the utilization of waste in concrete. So this was all from my side. I think now I'm open for the questions. Yeah, am I audible?
Yes, participants are requested to, whosoever wish to discuss anything more or wish to ask any question are requested to unmute yourself and ask the questions. We had a very thorough session, rather both the parts of the expert lecture or the theme session was very brilliant. So I thank the learned speaker and ask the participants to air their queries. Participants.
I hope there are no query. Any queries?
Good morning, Professor Choudhary, sir.
Yeah, good morning. Good morning, sir.
Sir, I'm Anil Kumar Sharma from Arya College of Engineering, Jaipur, Rajasthan.
Okay.
Sir, there is a basic query regarding as we have discussed in the first session, that we can use the construction waste as a replacement of aggregate really. So, sir, there is some amount of cement is already present in the aggregate of concrete waste aggregates, we can say. So it will affect to our mixed design according to the 10 that is 10.262 according to the IS code. So we have to adapt some measures to mapping with the amount of cement, because in the mixed design the cement of amount, and we have some additional cement amount in the aggregates as well. So overall, it will increase the amount of cement content if we are using the concrete waste. So is there any measures to manage the amount
Actually, like when
of cement according? Yeah.
no, actually that cement which is stuck there on the aggregates, that is not of much use because already hydration has taken place and other reactions have taken place. So it's a reverse way. Whenever we are using aggregates, we have to do some surface treatment so that we get neat and clean aggregates. So we have to remove all those stickings on the aggregate. And there are this surface treatment methods available in the literature. So we have to adopt one of those surface treatment methods. That cement is not like the same unhydrated cement. This is already hydrated.
Okay.
So this is not going to give much advantage to us. In fact, that will absorb water only, nothing more than that.
Okay. Thank you, sir.
Yeah, thank you.
Hello, sir.
Great. Good morning, sir.
Oh, good morning. Good morning.
Sir, I want to ask, can we use empty plastic refills as fibers to provide reinforcement in concrete? Also, what are the advantages or disadvantages of this method?
You want to use empty plastic bottles?
No, sir. Empty plastic refills of pans.
Empty plastic refills of pans. Actually, we have to see basically how does it affect the bond. The problem with the plastic is always because it's a sort of impervious uh, sort of material. So it creates an impervious sort of layer between the aggregate and the cement paste and the other parts of the concrete. So naturally, it is going to reduce your overall strength. But yes, it can improve your. It's going to reduce the compressive strength, but it can improve the cracks arresting property, and it can improve the flexural strength a little bit. But overall, it has to be studied. That's a good idea. And then again, what you need to see, it might happen that the complete length of that whatever you are using this waste pen, that the complete length might not be that useful. Maybe you have to see at different sizes which size is the optimum size.
Okay, sir. Sir, I want to ask
So,
another question.
hmm, hmm,
As you discussed the various tests like SEM,
hmm,
XRD,
hmm,
so
hmm.
where are these tests can be performed in our state or country, sir? In the laboratories, sir?
Like in Rajasthan, like in Jaipur, this yeah, in Jaipur, like Rajasthan University, these are in mostly they are available in the universities. In any established university which has science departments, they have these techniques and these equipments available with them.
Okay, sir.
That is
Thank you.
one.
Thank you.
Then mostly NITs and IITs, they have material research centers that is other. Then UGC has established certain centers which are exclusively for this purpose. Like in Indore, there is one center, and I do hope in Rajasthan also there might be one center where they are exclusively for this testing purpose.
Okay, sir. Thank you so much, sir.
And
Thank
yes, okay. Yeah.
Hello, sir. Good morning, sir.
Hello.
Good morning,
Yes.
sir. Sir, I am
Good
Sandeep
morning.
Vermaji from Odisha, sir.
Mm-hmm.
I want to ask you, sir, in the microstructural analysis, if we supposed to see the hydration compounds like CSH
Mm-hmm.
or CHS are the hydration
Mm-hmm.
compounds, can we quantify them? Can we get a quantifiable
Mm-hmm.
this much CSH has produced in this
So that
sample?
is very difficult actually. That is very difficult task that can be quantified, but mostly even qualitatively, if we see that, that's sufficient.
Yes, sir. Sir, another
Quantifying is
thing is,
quite difficult.
okay, sir. Thank you, sir. And another thing is, sir, the EPMA technique is there, sir. Do you know about this thing, sir? Any information is
No, no. Can you put in for electron?
probe micro analyzer?
Uh, no, I have not used that, so I'm not sure.
May I
Okay, sir. And
append
another thing, sir.
may I append here? The participant, I have used the PMA
Yeah.
technique, it can be used. Uh,
Uh, yes,
the
sir.
participant from Odisha may note that EPMA can also be used. Uh, Sorry, I interrupted. The participants and the learned speakers may carry on, sir.
No, no. It will means affect the concrete strength also
Okay, sir.
because it's a pozzolanic
Thank you, sir.
material.
Yes,
It's
sir.
not an inert material.
So, is it necessary to check the pozzolanic reactivity as per IS 1727?
Yes, you have to check the pozzolanic activity. There are two, three
Okay, sir.
methods available, na? Fraternity method
Mhm.
and all other methods you have to do. And
Thank you, sir.
one Mr. Sudarshan has written, okay, thank you, that any specific IS code available. There's no specific IS code available for adopting directly the waste, but recently the code fine aggregate has changed, and in that they have allowed some specific percentage of different waste in the concrete. Else you have to do your own protocols. Yeah, anybody else?
Uh, I think many of the participants have already asked the questions, and I am glad that your
Okay.
elaborate explanation has aroused inquisitiveness to know more, and even the young minds to ignite the young minds so that they are now thinking of doing some microstructure analysis, etc., as was seen in the remarks of Anil Sharma and other fellows. So it is very good that we get new researchers out of this FDP. So I, on my behalf and on behalf of Rajasthan Technical University, extend my heartfelt thanks to the learned speaker who spared time from his busy schedule. I requested him to prepone because of the centralized inauguration. So he acceded to my request and rescheduled his earlier commitments also. So I am very grateful personally to Professor Sandeep Choudhary ji, and uh, thank you very much, sir, and we request your patronage in future also. Thank you, Choudhary.
Thank you, sir, for giving me this opportunity, and I hope that we'll meet again soon.
So nice.
Okay.
Thank you so much. Thank you.
Okay. Thank you.
Thank
Thank you.
Thank you, all participants. We meet again in the centralized inauguration ceremony arranged by the AICT at sharp 11 o'clock. So we meet again, and then second technical session by Professor Saroj Mandalji from Jadavpur University on geopolymer concrete shall start at 11:55 a.m. So please join us in 11 a.m. session as well as 11:55 a.m. session. Any participant if wish to ask anything, he or she may ask at this point. Any participant wish to ask anything about this FDP? As has already been shared that feedback links will be given on the last day of the FDP. All participants are requested to fill the feedback on their AICT portal mandatorily. AICT will issue the certificate only to those who fulfill the three conditions. One is minimum 80% attendance, minimum 60% marks in the quiz or the test conducted on the last day by the coordinator, and third is the feedback submission on the AICT portal by the participant. A feedback form, Google form, shall also be circulated by the coordinator, that is me, on the last day, so as to be submitted by you people. And you are also free to benefit me through your feedback on the WhatsApp group as well as personal emails to improve the sessions. Thank you all. Meet you again at 11 a.m. Thank you.
Thank you, sir.